The magnetic field at point P due to circular current carrying loop is given by B is equal to mu naught I A square divided by 2 times A square plus X square to the power 3 by 2, where A is the radius of the circular loop carrying current. Now, I want to increase the magnetic field at point P. So to increase the magnetic field at point P, what I can do it? Here you see this magnetic field completely depends on I, right? It depends on current. If you increase the amount of current passing through a conductor, the magnetic field at point P can be increased. Now I want to get very strong magnetic field at point P. Very strong magnetic field I want it. For that, what we need to do? We need to increase the current. Very high current we are going to pass. Of the order of mega amps of current we can pass it, right? Maybe if it is possible to supply the current of mega amp around 10 to the power 6 amps, do you get very high magnetic field at point P? Let us check it. To check that, again I am taking this formula. It also depends on the quantity mu naught. It also depends on the quantity mu naught, and I is also there, right? And this mu naught quantity, this is the value of mu naught. The value of mu naught, you already know it. This is around 10 to the power minus 7, right? And though if you supply a current of 10 to the power 6 amps, how much you are going to get the magnetic field? It is drastically reducing. The product of mu naught and I is reducing, right? Though if you increase the current. So now the question is how to increase the magnetic field at point P. And one more disadvantage of increasing current is that heating effect of electric current. That means the more and more current if it is flowing through a conductor, it gets heated up. Finally, it leads to melt the wire itself, which wire we are using, it will lead to melt. So we cannot able to increase the current. It has a limitation, certain limitation. Then what we can do? Is there any other option? Yes, we have one more option just by increasing the number of turns. Increase the number of turns of the coil, then the magnetic field also can be increased. So instead of using only one turn, I am going to use many number of turns. Many number of turns are very closely spaced. These turns are very closely spaced. So as the n value increases, if n value increases, the magnetic field at a point P also increases. So instead of one turn produces one magnetic field, say, and B units it produces. And if two turns, three turns, four turns, then it becomes 2B, 3B like that, right? And if you increase the number of turns to million number of turns, 10 to the power 6 turns, if you increases, then magnetic field also increases million times. So the current has its own limitations. If the current increases, there is a disadvantage. So but we can able to increase the number of turns in it. And this particular device, what you are observing here, this is called as solenoid. We will call this as solenoid. Then what is a solenoid? The solenoid is a piece of equipment is used for generating a strong magnetic field, and this is called as a solenoid. Solenoid is nothing but take an insulator, just an insulator, and wound certain number of coils, wind the wire, straight wire on this insulator. So many number of turns you are going to get, and this device is nothing but a solenoid. It is used for producing very high magnetic field. Okay, this is the solenoid you are observing. So these are the number of turns wound in the form of helix. So it is wound on the insulator. And now there is no magnetic field at all in a solenoid because there is no current is passing through it. Now pass the current. The current is going into the turn, right? It is coming towards me and going, coming, going, right? It is going, coming here. Okay. So it produces a magnetic field. The magnetic field pattern is like this. So the magnetic field almost outside it is very low outside the solenoid, but inside the solenoid it is very maximum and very high magnetic field you are going to get along along the solenoid. But outside it is almost very low. That is negligible magnetic field you are going to get outside. But inside the solenoid, the magnetic field is high in number. Number of field lines are very high. Therefore, magnetic field is also high. And that magnetic field here, this magnetic field is given by B is equal to mu naught Ni, where mu naught is permeability of free space. So mu naught you can write it here if the solenoid, inside the solenoid there is no other material, magnetic material, only air or vacuum is present. But inside the solenoid, if you place any of the material, maybe ferromagnetic material or any material, if you place it here, then we have to write it as mu, where mu is permeability of that ferromagnetic material we are going to take. So this magnetic field can be written as mu naught Ni, not mu naught here, it is just mu Ni. If the solenoid, the core of the solenoid is filled with a ferromagnetic substance. So greater the value of mu naught and greater the magnetic field you are going to get. So greater the value of mu, greater the value of magnetic field. That means the ferromagnetic material having high value of mu produces very high magnetic field. And this magnetic field also depends on N. N means the number of turns per unit length, and I is the current passing through the solenoid. And the current is passing through the solenoid. For the observer standing here, it appears like it is south pole. For them it is south pole, and the observer standing on the other side, other end of the solenoid, for them it appears like a north pole. As a result, the solenoid, current carrying solenoid, always acts as a bar magnet. Solenoid is equivalent to the bar magnet. Remember it. Now we have some idea about the solenoid. So here there is a solenoid. So it is very simple. It is just a coil. It can be just described as a coil. That is a solenoid. And it produces a magnetic field, we know it. That depends on the core of the solenoid. The core of the solenoid, that is core means inside the solenoid, inside these turns, you place any of the material. It may be insulator, it may be just air, or it may be any ferromagnetic material. Depending on the material we are using, the magnetic field varies. To get very high magnetic field at a point, we need to use a ferromagnetic material having very high permeability value. Iron has some high value of permeability. So if you use the iron as a core of the solenoid, then you are going to get very strong magnetic field. So keep the iron material inside the solenoid and pass the current in it. Immediately this becomes magnetized. the iron becomes magnetized and picks some of the iron material kept towards it. Depending on the current and depending on the permeability of the material used as a core, the magnetic field can be decided. To get more magnetic field, keep ferromagnetic material. So pass the current in a solenoid and very strong magnetic field you will get it. So you can ask, what is the use of solenoid? Why we are studying it? Before coming to that point, one more device is there that is called as toroid. The toroid is nothing but a circular form of solenoid. Just take a solenoid bent into circular shape, that is called as toroid. Okay, this is what the toroid you are observing it here, and this is also used for producing very high magnetic field. Compared to this solenoid, the toroid can be used for producing even high magnetic field. So the toroid is hollow circular ring on which a large number of insulated turns of metallic wire are closely wound. This is what you are observing it here. This is a toroid. And the magnetic field inside the toroid, we can able to find it out, and that magnetic field is also similar to the solenoid. Mu naught Ni. Mu naught is permeability of free space, N is number of turns per unit length, and I is the current passing through the toroid. And these two devices, equipment, were found by Ampere only. Ampere found it. So where do we use a solenoid or a toroid? Some of the few applications we can see in our daily life, we are using the solenoid even in a transformer. Transformer, that is our mobile charger, laptop charger. Inside that charger, we have a small transformer, and that transformer is step down transformer. We are using it. There also we are using a solenoid, and we are using the solenoid as or toroid as electromagnet. Electromagnet are used for producing very high magnetic field. And what is electromagnet? The electromagnet here in the same figure you can see in the figure, this is an iron. Suppose this is an iron core. It is made up of iron core, and on this iron bar there is a coil which is wound, right? This is a solenoid. And I will keep some magnetic material over here. These are the magnetic material, maybe such as iron only. Iron materials are there. Now there is no current is passed in it. There is no current passed in a solenoid. Then these iron particles will not experience any attractive force. Now if I pass the current through the solenoid, what happens? This iron becomes immediately magnetized. When it becomes magnetized, what happens? These irons start attracting towards the iron bar, iron core, and this phenomenon is called as electromagnet. Now immediately if you stop the current, these iron material were attracted will fall down. So when current passes, it becomes magnetized. When the current is stopped, it demagnetized. So that is called as electromagnet, and we are using these solenoid in medical clamping equipment. The same principle will be applied over there, and automotive gearbox we are using it, and simple locking device. Many more applications are there based on the solenoid and toroid.